Okay, Associate Professor Dr. Fadli, the head for Central Lab of the entity. And all of our guests, welcome. Representing the School of Fundamental Science, because unfortunately our NC cannot make it this morning, so I have to welcome all the participants and also the guests from abroad. And the organizing committee of the seminar, I would like to personally welcome each of you to this seminar and to your entity. It is known as campus by the sea, because the sea nearby our campus. We are delighted to have you here to participate in the second PRC Distinguished Lecture Series, Fibers Sensors for Landslide Monitoring, co-hosted by University of Malaya and University Malaysia Terengganu. Thank you for coming. We are honored to have Professor Ulung Dato' Ali Ahmad. I think everybody recognize him, right? The latest Professor Ulung appointed by Malaysia, by our negara. Okay? We are lucky because he's here today with us. You are very popular. Everybody wants to be next to you. And then again, Professor Kennenth Freng, Professor Azur Rahman, and Professor Kidunto Pramila with us today. All four individuals are esteemed specialists in Photonic and using fiber sensors for landslide monitoring. We thank you for sharing your expertise with us at UMP, especially regarding landslide monitoring. And we are pretty sure we'll be inspired by your presentation and achievement in this field. Realizing that UMP is a relatively new university, so it's an exciting time for UMT to be invited and involved in this event with or University of Malaya, particularly discussing the topic which is very close to our heart, beach erosion nearby our campus. Our beach is confronting a time of many changes, and we are experiencing worries about what is going to happen to our campus and its environment in the near future if the current problem is not solved. So we hope that the seminar, as well as the presence of these prominent speakers from abroad, will open new ideas to the problem solving by engaging ourselves in research collaboration in these specific or related fields. Collaboration with international expertise is our target to be more visible globally. As before I hand over, because I have to say, not very short speech. And before I hand over to Mr. Chairperson of this morning event, I'd like to thank each of you for attending this seminar, and to again Dr. Hadir for bringing the experts to this gathering at UMT today. I want to say once more on behalf of the UMT committee and also the organizing committee, welcome. It's a pleasure to see so many of you here, and I wish a pleasant and fruitful meeting, and to the speakers abroad, have a pleasant stay in Terengganu. Thank you.
Thank you very much, Professor. As we all know, today we are very fortunate to have with us the 2014 Malaysia Distinguished Professor. Therefore, before we begin the lecture series, it is my pleasure to cordially invite Distinguished Professor Dr. Harif bin Ahmad to say a few words. Let us put a hand together for Distinguished Professor Dato'.
chairperson for this session. In fact, I'm very grateful that Prof. Nakisa agreed to co-host this event at UFT. We had the first event in Kuala Lumpur last year. So this year we said to ourselves, why not we come to Terengganu and see the erosion problem? Because the grant was given to us under British Council, Newton Rumah Fund, £150,000, with collaboration with Professor Azizur Rahman. So this on environmental issue like pollution, landslide and so on. So once we are here, we can, I think Prof. Kennenth and promised us to solve the erosion problem. So we give a clap to him. There will be no more erosion in UFT, because I was being told UFT is slowly the land are moving away to the sea floor. Eventually, after 3 years back, you don't see this building anymore. So Prof. Ken has promised us that he will solve this problem. We have met the Vice Chancellor. I think we are very interested to form a very effective collaboration. We have a new grant for this year with Ken Grattan on erosion monitoring. And I see a lot of physics staff here. I think also you're most welcome to join us. And take this opportunity to interact very closely with Professor Ken Grattan, one a very well-known figure. Prof. Azizur Rahman is a very well-known person, especially very good in getting money. For instance, Erasmus funders, you may want to talk to him. You may have one project, because he has been focusing in Kuala Lumpur all the time. I think you may want to look at VFT to apply some of the Erasmus project. And also Prof. Dibato, he's a very distinguished professor from Southampton. I think we should take this opportunity to interact, to ask them questions, need any advice, please do. And I'd like to thank the members of our group. A lot of the year from our members of the group, Prof. Faizal, Dr. Zulakimi, Dr. Sada, Dr. Afiq, and all our postgrad students, because this is our, not family day, our breakaway. So we never have the opportunity to have a breakaway. We planned many times, but we never get through. But this time we take the opportunity to come here. And thank you very much. In fact, I'm very grateful to Prof. Nakisa. Thank you very much.
Thank you very much, distinguished Professor Dr. Harith Ahmad, for the speech. And I also would like to welcome the members of PRC from to your family day here. But I don't think by listening, usually people don't listen to talks, to lecture during the family day, but you guys are very good coming here to listen to talks as your family day. Maybe we should try that. Right. Ladies and gentlemen, our second PRC Distinguished Lecture Series today has just begun. So we can now move on for our series of talk by our distinguished speakers. So before I invite our first eminent speaker, allow me to introduce his background. Professor Kenneth Grattan was born in December 9, 1953. He graduated in physics from Queen's University, Belfast, with a BAc First Class Honours in 1974 and PhD in laser physics. His research involved the use of laser probe techniques for measurement of potential new laser systems. Following Queen's in 1978, he became a research fellow at Imperial College of Science and Technology, sponsored by the Rutherford Laboratory to work on advanced photolytic drivers for novel laser systems. This involved detailed measurement for the characteristics and properties of novel laser species and a range of materials involved in system calibration. In 1983, he joined City University as a new blood lecturer in physics, being appointed Professor of Measurement and Instrumentation in 1991 and Head of Department of Electrical, Electronics and Information Engineering. His research interests have expanded to include the use of fiber optics and optical systems in the measurement of a range of physical and parameters. The work has been sponsored by a number of organizations with whom a joint patent for system for monitoring in the water industry is held. He obtained a DSc from City University in 1992 for his sensor work, and Professor Grattan is extensively involved with the work of the professional bodies, having been chairman of the Science, Education, Technology of the Institution of Electrical Engineers, the Applied Optics Division for the Institute of Physics, and he was president of the Institute of Measurement and Control during the year 2000. He was also awarded the Calendar Medal for the Institute of Measurement and Control in 1992, and the Honeywell Prize for the work published in the Institute Journal. Professor Grattan has been Deputy Editor for the journal Measurement, Science and Technology for several years and currently serves on the editorial board of several major journals in his field in the USA and Europe. In January 2001, he was appointed editor of the IMECO journal, Measurements, and also serves on their journal council. He is the author and co-author for over 500 publications in major international and conferences, and is the co-editor of a 5-volume topical series on optical fiber sensor technology. It's a long CV, yeah? Finally, Professor Grattan was the Dean of School of Informatics and the Dean of School of Engineering and Mathematical Science, and currently he is the Dean of City Graduate School, City University London. With the introductions, I'd like to welcome our first speaker, Professor Kennenth Grattan, to deliver his lecture.
So, good morning, everyone, and okay. So, good morning, everyone, and thank you very much for that warm welcome and review of my life over the last number of years. It's amazing what you seem to be able to define quite a number of things that have been involved. So today I'd like to talk about optical fiber sensors and look at some of the problems in industry where optical fiber sensors provide solutions, and then on the basis of that to be able perhaps to think with you about some of the ways in which we can apply some of the techniques or some of the ideas towards the problems of coastal erosion and some of the issues that are involved there. Work at City is mostly carried out with my colleague Professor Thomas Stern. We have been working together for many years, and we look at the ways in which we can apply a range of physical and chemical techniques to solve some of these problems. So I'm going to say a little bit about City University London, the home of myself and Professor Rahman, just to give you a little bit of background to our university. I think with the fact that we have a broad audience, I'll say just a little bit about optical fiber sensors and the contrast between optical fiber sensors and electrical sensors. And then I'll take perhaps about 4 or 5 examples and give you a sense of some of the work that we've done in solving industrial problems. And then perhaps it will help us to think how we might be able to apply some of the same types of solutions or the same type of approach to some of the problems that there are around landslide and coastal erosion problems here, and then a little bit about future directions. So, City University, we are an institution which dates from the 1890s. We were established on our site in central London in 1894, and we were established really for the basis of teaching engineering and associated technology. I think the main thing about the university is that we, in our background, we've been teaching electrical engineering and indeed electrical engineering and applied physics together since that time. And I think that's relatively unusual and reflects something of the focus of the university around problem solving. The electrical engineering department, which as you heard in the CV that was read out, was one which I headed for many years. But in fact, it was one which was established as electrical engineering and technical physics. And I think that is really a perfect combination of using the skills that you get from electrical engineering, applying some of the fundamentals and some of the new technology that comes into electrical engineering from discoveries in physics. And in that way you can really take forward the solution to a whole range of problems. And if you think really of the developments in the 20th century, so many of those were driven by looking at new physics and then taking that new physics forward into creating solutions which have influenced profoundly the way of life that we have at the moment. And it's almost impossible to envisage the world that we live in without that world having been influenced by fundamental discoveries in physics, particularly in the 20th century, but indeed some of them going back to the 19th century. And with that, of course, you see some of the great entrepreneurial opportunities that have come as a result. We've seen, particularly in the development of IT, we have seen people who have vast sums of money from exploiting some of those opportunities. And of course, we're very familiar with some of the names that of people who have done that. But if you actually look back then and you think about some of the great scientists of the late 19th and early 20th century, someone like Lord Kelvin, who is so familiar to us from the Kelvin scale, was really a very entrepreneurial physicist. He worked very much in the field of communications. He worked on the early transatlantic cables and solved many of the problems which led to the first the transmission of the telegraph and then the telephone across the Atlantic using effective cables. And in so doing, by being involved in this from the start, made himself a lot of money. So being an entrepreneur is not new. It actually goes back really quite some time. So potentially, I think a lot of these problems that we're dealing with are ones where if we take new physical opportunities, new things that come through from physics, then there are some really interesting ways in which engineers can then apply these, and I think potentially both solve problems, make society better, and as well, there are some really good opportunities for entrepreneurship as well. So that's just a little bit about a background and so on. But we've been City University since 1965, and formally later on this year we become part of the University of London. So it's just a slight change in our status. 100 years ago, our students looked like this. This building still exists. It's our main building in central London, and this is a very old London bus. of the type that was around at that stage. And these are some of our students hanging off the top of the bus. They look very, very strange. And in fact, I think this picture is a picture from the what's called the Bragg Day. It's a day when students dress up and go out and raise money for charity. And I think that's the reason for the bus perhaps having been hired to take them to do that. And it's an interesting picture to find. We move forward, of course. This is the 1950s, the traditional type of image of machining and so on that you see. And of course, my background, as you heard, is very much in lasers. And I always like to say that this is an interesting picture of laser systems. The health and safety issues are such that it would be impossible to take this picture in the United Kingdom, and this was not taken in the UK. There are lots of interesting reflections of some quite high power lasers there. But it does remind us that photonics really is a fascinating area, and one where there are so many opportunities. So City University today, this is that same building as it looks today. We have about 20,000 communities. As you've heard, our research work is concentrated in the School of Mathematics, Computer Science and Engineering. And we're a very international university because of our London location. And we have lots of staff and students from across the world. We have students, in fact, from 150 countries across the world. So if you think the United Nations has about 200 members, we have about 3/4 of the United Nations at City University. So, as I say, about 100 years and more of engineering education, and of course we bring to that mathematics and informatics, which really forms the key with physics, mathematics, informatics, and engineering, really the key to the solution of today's problems. So let me just mention just a little bit about photonics and optical fiber sensors, and just provide a link perhaps for those of you who are less familiar. And really the key thing is that in photonics we use photons, where in electronics we use electrons. And in that way we exploit the properties of photons so that we can then do things that are either difficult to do with electronics, or else where electronics perhaps doesn't really provide us with the best solution. But optical fiber sensors really are photonics devices. They're devices which use lasers and LEDs. They use transmission of light along optical fibers, using the basic principles of physics that underpin the transmission. And in that way we're able to make optical analogues of some electron type systems. So if you think about it, the electron is a fundamental unit of charge, of course. It's got a small mass, and it travels along a cable in the way in which we're familiar with. And you can look at the parallels between the electron and the photon. It's a fundamental unit of light, but there's no mass, and of course it travels along insulators in the same way that electrons travel along conductors. And of course we're transmitting information at the speed of light in that medium. So and the medium is typically glass with a refractive index of around 1.5. So you can see you get a reduction in the speed of light in vacuum by that factor. But it does mean that you can transmit information very fast, and of course we're familiar with that with optical fibers used in communication systems, because that's the way in which we get the quality of communication that we have at the moment. So optical fiber is very important. I'll be dealing with sensors using conventional optical fiber. In many ways, the same type of optical fiber is used in communication systems, or fiber that's relatively similar. And I'll show some of the differences perhaps as I go along. And Gilberto will mention a different type of fiber in the presentation that he gives. And in that way, you can see the parallels between the use of communications type fiber for optical fiber sensors and some of the new microfibers and the potential that they have. So what it shows, I think, is that optical fibers in sensing it's not just a sort of straightforward and single sphere of work, but in fact one where there is considerable breadth. And I hope by the end of today, as you hear about some of the practical work that we've been doing, you hear from Professor Roman about some of the ways in which you can model the interactions between optical fibers and the outside world, and understand the way those interactions work, and then use those in design. And then some of the microfibers that Gilberto will talk about, you'll get a sense of the breadth of the subject, and in that way understand how some of the problems that relate to the issues that we have in the Newton Fund then can be solved either through experimentation or through simulation, and ideally, in fact, bringing together the work in simulation and experimentation to create the breadth of the study. So why are optical fiber sensors really of interest? And I would suggest that perhaps the key thing is that optical fiber sensors are used in particular for specialist applications. If you want to measure temperature, if you want to measure the temperature in this room, then they're probably the simplest and easiest way is to go and buy yourself a small standard thermometer, or buy yourself a thermocouple or a thermistor, and just connect it up. And for a very small sum of money, you'll be able to measure the temperature in this room. And indeed, I suspect that the air conditioning and so on in this room is the control loops and so on are done through the use of that sort of technology. So for most applications, most straightforward and simple applications, there are many conventional solutions available. They're well established. They're relatively inexpensive, and so from that point of view, there's no need to think about using other technology. But there are situations, for example, where you may wish to measure temperature, where you have a number of constraints, and that's where thinking about the use of optical fiber sensors is something that makes a difference. So, for example, you may wish to make measurements of temperature or pressure or strain or chemical parameters where using electrical monitoring is unsafe. And that could be unsafe because of the fact that there is, say, a risk of sparking. If you get a short circuit, then you would get a spark, and that spark might ignite an explosive gas. And in that sense, you could then cause an explosion through the use of an electrical technique. One of the perhaps familiar areas where that is a problem is in making measurements in sewer systems. There's a problem there with the buildup of methane. Methane is natural gas, it's an explosive gas when mixed with oxygen. And there have been many reports over the years of explosions within sewers as a result of electrical sparking occurring, and you can do enormous damage and create a lot of loss of life from that sort of problem. So it's just one example of where the use of electrical sensors because of sparking can become a problem. Measurements in mines, for example, are problematic. We work with the Shandong Academy of Sciences in Jinan in Shandong province in China. They have been installing optical fiber-based methane sensors because of the problems of measurement of the buildup of methane in mines. China has a particular problem with a very strong dependence on the use of coal for its power stations, but also it has a number of mines, some of which are quite old, some of which where are mines where the safety problems are not well dealt with. And so there is a real need to measure the buildup of methane in mines because of the risks that are involved to people, both of the gas itself and from the explosion risks of the gas. And there we're working with them on the technologies that relate to methane sensing, to measuring humidity, to measuring other parameters in mines, to make them safer. Secondly, there are issues around where electrical monitoring is unsafe. And in that case, there are situations where there's perhaps large amounts of electromagnetic noise. If you have a lot of noise, you have problems with pickup with electrical sensors, and so it's not a good situation for monitoring. And so you will want to look for other techniques that will enable you to measure where there's a lot of noise. Third situation is when there's a large number of sensors to be placed, and I'll give you an example of that in the talk a little bit later. But if you have sensor numbers going into the hundreds, and if you consider the number of wires that you have to connect, if you consider that you're trying to perhaps make measurements over distances over hundreds of meters or kilometers with hundreds of sensors, then there are major problems with connecting up very large numbers of wires. There are major problems with signal fading. Lots of difficulties in trying to put these sensor networks together. And optical fibers offer, in many ways, a better solution. And I hope I'll convince you of that before the end of the talk. Optical fibers as well are relatively lightweight. An optical fiber is the dimensions of a human hair. So from that point of view, if you think about the impact that makes on something that's relatively small, by comparison, say, to the use of a conventional electrical connection, then you can see that optical fibers do have a particular advantage. And so, again, the light weight of optical fiber sensors is something that is particularly important. And I think finally I would suggest that with optical fiber sensors you can have really a competitive cost for the use of these sensors. As I say, you want to make a measurement of temperature that's associated with the air conditioning in this room, then an optical fiber sensor is not the way to do it. It's not going to be competitive in terms of cost. But if you're looking at the use of, say, a number of sensors, or perhaps even hundreds of sensors, then you can make these systems competitive in terms of their cost. And particularly where there are issues around safety, then cost becomes quite different really in terms of the considerations that have to be done. So optical fiber sensors can be competitive in terms of their cost and the benefits that they offer. So let me also divide optical fiber sensors into a couple of categories just to give you a quick way of categorizing them. There are both extrinsic and intrinsic sensors, and if you look at extrinsic sensors, then typically an extrinsic sensor is one where you have a light source, an optical fiber connected to some form of light modulator, and then from that light modulator you have another fiber connected into the detector, and the environmental signal then interacts with the light modulator, and in that way you create the effect that you measure. In the intrinsic sensor you have the same connection, but actually the interaction occurs within the optical fiber itself. So therefore, within the fiber, what you have is really what's going on. You have the transducer, and in that way you create an optical interaction, which is then measured using the detection system. This contrasts with the use of optical fibers in communication systems, because in communication systems what you want is essentially a straight transmission from here through the optical fiber to the detector, and no interaction. But in optical fiber sensors, you actually want the opposite. You want that interaction, because it's that interaction which gives you the sensing capability to respond to the environmental signal. And so many of the issues that were dealt with optical fiber communication systems, which were causing problems, were actually opportunities for optical fiber sensors. And in that way, we in the sensor community are able to take some of the difficulties that are experienced within the optical communication systems and use these to our advantage. A number of our sensors use fiber Bragg gratings, and fiber Bragg gratings are a diffraction grating written longitudinally within the fiber. And we do this with the use of a laser, an ultraviolet laser shining through a phase mask, which brings an interference pattern, which we can print within the fiber. And if you look at the way it works, it's typically like this. And if you pass a broadband signal through the optical fiber with a grating in it, then it cuts out a small part of that spectrum, and the wavelength or color of that reflected spectrum then is an indication of the characteristic, and that you can measure. Now, if you then take that same grating in the fiber and you then change the characteristic of it, for example, you stretch it as a result of the use of a temperature or pressure or strain or humidity, something like that, then that stretching changes the wavelength that you get coming back. And in that way you can then pick up a slightly different signal. And so you can relate that, that perturbation, that change, to the change in color. Just going to grab one of these things here, which will then give me some. It does a trick. There is a straw. Great, and then perfect. Good. That helps. Right. So we have the characteristics of the optical fiber grating. So we've done a number of different things along the way, and I won't dwell on all of them because there simply isn't time. But just to say that one of the things that's I think particularly relevant to the issue of coastal erosion, the issue of protection of against landscapes, are perhaps some of the work that we've done on safety monitoring in relation to steel and composite bridges and concrete foundations, because we've put optical fiber sensors into some of these different types of structure, and I think there are many parallels to the solution of the type of problems that we have here. This is a rather nice bridge. It's a 350-meter concrete bridge in Norway, and we put some optical fiber sensors in the middle of this to monitor the strains due to the traffic. So the sensors were installed within the bridge after it was built, and we were able to monitor quite nicely. This is a much smaller bridge. It's a 10-meter bridge. It's not designed for traffic at all, but in fact for people. Although on the opening it was, you can see that it had a rather heavy piece of traffic through this tank, which was used just to illustrate how strong it was. This is made out of composite materials, and our sensors were actually installed. They were built into the bridge when the bridge was being designed and built, and so they're in the middle of the bridge. And again, we can measure the strains. This was done some years ago, and those sensors are still there. And some of our colleagues from the University of Birmingham have visited this bridge several times and made some measurements, and most of the sensors are still working. A few of them are actually physically broken, but it shows that you can install them in a situation like this and use them after many years. And the third is in foundations. If you build buildings in London, for example, you typically need very deep foundations, and you end up pouring very large quantities of concrete into the ground. So if you have a new building, often the cost of a significant part of the cost of the building, I think a quarter or something like that, often is in relation to the cost of the foundations. So if you knock that building down, and many buildings are built now only to last for 20 or 30, maybe 50 years, something like that, and then they're replaced. if you don't have to replace the foundations, that can be a considerable cost saving. And we put optical fiber sensors into the foundations to measure the conditions in the foundations of the building. So typically a fiber Bragg grating will give you a response like this. This is on the Norwegian bridge. This is the response of a resistive strain gauge, and this is the response of the optical fiber. And you might think that this is just a little bit of noise perhaps that's crept into the signal. But in fact this is the result of a truck running across this bridge. And what you're getting is a sort of bounce of the truck axles. And so you get an increase in strain and then a decrease in strain as you go through that, and then the major increase for the weight of the truck. And as the truck continues, you have this higher level of strain from the weight of the truck on the bridge. So you can get results that which parallel very well the results you get from the resistive gauge. You can get more information, and of course this is just from one gauge, and you can put many of these gauges, connect them in a network across a bridge of several hundred meters. So I think this is one parallel with the situation we have here, where you want to make measurements over, I'm sure, many hundreds of meters. So optical fiber sensors joined together in a network work very well under those circumstances. This is the situation with the composite bridge. These are the materials of which the composite bridge are made. And our optical fiber sensors were inserted in between these pieces of composite as the bridge was put together. We had only about 2 millimeters or so to try and squeeze the sensors in, but that wasn't the problem, and we were able to put them in as this bridge was being built. This is the inside of a bridge. It's a box section, well, rather similar to a room like this. And if you imagine if there were cracks in this wall, then basically this is the problem that you have with this concrete platform bridge, that it has cracks because after 30 or 40 years, then you begin to get problems with the degradation of the bridge due to cracking. So what you can do is you can put patches on it, and these patches are made from carbon fiber, and you can then put, in some of these, you can put optical fibers, and those optical fibers will help you to measure the strains on the repaired bridge, and help you to avoid excessively straining the bridge, so that you don't end up with more problems than from cracking that's continuing. This is another bridge here that we looked at. This is one that which we had access to. It's a 1950s railway bridge in Sweden. It's a concrete bridge that was taken out of service, and you can see that this bridge has been loaded, and you can see the major cracks that have been resulting from the loading. But before this bridge was loaded, we put some optical fiber sensors into it to monitor what was happening. And this is the technique that we used. We took some carbon fiber reinforcement bars, and we put an optical fiber inside those bars, and then inserted those within the bridge. And the technique for doing that is as follows. This is the carbon fiber reinforcement. You cut a groove in that. You then glue the optical fiber sensor into it, drill a hole in the concrete, and then insert the tube into the structure. And then the optical fiber within that reinforcement bar is used to provide strengthening. In the case that we had, what we did, of course, was we were actually loading this to destruction because it was an unusual situation. The load there is a load of 10 meganewtons, and we're very easily able to measure that load and the strains that were created. But you can use these techniques in the repair of bridges, and that way to maintain them over many years. One of the things that you might think about with optical fiber sensors is, well, optical fibers are very delicate. You know, if you're doing work in a laboratory with optical fiber, then you know, you're dealing with something that's delicate and something where you want to keep them in a nice, clean and dust-free environment. But in fact, one of the things you can do with optical fiber sensors is to install them in concrete. And this is some work we did with a commercial firm that makes precast concrete pieces. If you think about, for example, concrete lampposts, if you think about concrete railway sleepers, there are an awful lot of standard precast systems available where you use concrete, you make certain pieces, and you make these by the 100 or the 1,000. And there are commercial companies like Grey Concrete which do this. And for some of these, you want to measure what's actually happening within the concrete. And this is a floor panel, so you can see it's a fairly large one. And what we've done is we build these up through, we build a cage of reinforcements using steel, and then we put an optical fiber and then optical fiber sensors using Bragg gratings to measure the strains. And you can see the yellow optical fiber running all the way along the reinforcements here, and then this cage is then filled with concrete. So this is the factory here. You can see these are the workers here who are involved, and this is the production lines. And so this is one of these large devices being built, and then what we're doing is we're pouring concrete onto this cage. So this is nasty wet concrete that's being poured onto the cage to make the panel. If you look closely, you can see the panel here, and coming out of it is the optical fiber itself. It's just the yellow there is the plastic coating on the optical fiber, and we have a couple of connections here just being held up while the concrete is drying. And then this is the sensor here, the connection to the sensor, which is inside the concrete here, and we're just protecting it with a simple plastic bag. So you can use these optical fiber sensors in concrete to make measurements. And this is one of the important things that links into our problem of landslides and erosion, that I'm sure there are going to be situations where we want to do the same. Another problem with concrete is the energy that concrete uses. If you manufacture concrete, as major countries across the world do, then there's a vast amount of energy used in the manufacture of concrete. It is very, very energy consuming. And one of the ways of trying to reduce that is to cure the concrete, to make the concrete set under situations where you use different types of setting rather than just using conventional heat. And we're working with some colleagues at University College in London and with a couple of commercial companies to microwave concrete. If you think about the use of microwaves, say, to heat food, you can use microwaves to heat concrete and make it set faster. And the main difference is that you need a rather larger oven. This is a commercial microwave oven. You can see from the comparison with the worker here just how big it is. So you can cook a lot of food in that, and indeed I believe our colleagues in the company have demonstrated that you can cook something. If you take a large turkey or something like that, which won't fit into a conventional microwave oven, it fits beautifully into this, and they have cooked it, and I'm told it's very good. So we're cooking concrete, and for the purposes here of test, we're using standard cubes of concrete. But an oven like this, and indeed a bigger oven, really is planned for the curing of devices such as concrete sleepers for railway systems. You know, they're that sort of size, and they fit very well into an oven of that nature. So what are we doing? This is our colleague who runs industrial microwave systems, Bob McKinnon, and one of our looking at monitoring of the signals from the fiber Bragg grating that we put into these concrete while it's being cured. And that's the standard block, and this is our optical fiber sensor. It's a little hard to see, but there's an optical fiber sensor just coming out here. The approach is this one here. We have in this case we've got simply 5 fiber Bragg grating sensors in the center of this cube, and you can see it coming out here. These are standard blocks that civil engineers use for testing. This mold here is made out of plastic, because if you think about the fact that within a conventional microwave oven in the kitchen, you don't put metal objects into it. So again, with this, you don't use a metal case, but you use a plastic one, and you can use plastic or ceramic. In our case, we use plastic to produce these standard blocks. And that's our fiber Bragg grating temperature sensor, just here. So these are the sorts of molds that we're comparing with. This is the plastic mold that we use for the microwave. This is these are 3 steel molds, and what we do is we cure them at 60 degrees using steam. So this is the conventional industrial way, and then these 3 were cured at room temperature, again in the steel mode. So we were able to compare steam curing with room temperature curing with microwave curing. The interesting thing about the microwave curing is this, that you can monitor the temperature, and these are the outputs from the 5 sensors. You typically want a temperature between about 60 degrees and 70 degrees in the concrete. If you go too high, you'll start to boil the concrete, and you'll end up with the same problem as if you put say you put an egg in a shell into a microwave oven and heat it, it will explode, and you'll basically get the same problem. You'll get this sort of internal explosion of the concrete, which destroys its quality. So you want to keep it at about 60 to 70 degrees. The black line is the power profile, so it's the way in which you can put power into the system. And just like your domestic microwave oven, where you can turn it on for a second or 10 seconds and then turn it off if you like, then with the microwave power, what we end up doing here is we have a burst of power, and then we turn it off, then another burst of power, and so with the feedback from the control system, you can see that mostly the microwave oven is off. So we're maintaining the high temperature, in fact, by minimizing the amount of energy that we're putting into the concrete from the microwave oven. And so it's very, very energy efficient because of the fact that we have the oven off most of the time. If you compare that with the way you might do it with steam curing, you're then passing steam continuously over the concrete sample, and so you're generating steam at above 70 degrees and passing that over, and so you have a lot of energy needed to generate that steam. And these are some measurements of the compressive strength. We had a meeting just last week of our consortium, and there is some new information that's come through from the tests that are being done. But there are two tricks that we've used here that supplement the use of microwaves to produce very low energy consuming concrete. This concrete contains 25% pulverized fly ash, and this 55% pulverized fly ash. Fly ash is a waste product from coal-fired power stations. It's a waste product, and there's a real problem getting rid of it. But it's a very good material to put into concrete because it reduces the amount of cement that you have to use. So if you've got 55% pulverized fly ash, you only have 45% cement. And cement is expensive when you're building very large buildings. So therefore, you're reducing cost. In addition, you're reducing energy. The pulverized fly ash is a waste material, whereas cement is a material you have to manufacture and use energy to manufacture. So this is the one that we're particularly focusing on. And you can see here that looking at the compressive strength with both room temperature curing, oven curing, and microwave curing, you're getting very similar levels of strength. And in fact, that's showing a strength of around 4 megapascals. At our meeting last week, our colleagues were using a new formulation of cement, and they were able to get strength up to 15 megapascals. That is very, very important because our industrial partners were then able to say the strength of that concrete is the right strength that we need for the production of the types of precast elements that we produce. So they're able to get concrete of the right strength, which used a lot less material, and as well used microwaves to cure it. So the whole energy efficiency of these new samples was very, very much better. And this is just a picture of the energy efficiency of the samples here, comparing conventional with microwave and conventional with microwave for the two different types of fly ash. So it's a very efficient way of making concrete. And so what you have here is high quality using the optical fiber sensors in a way that you can't do with conventional sensors, and at the same time to obtain a very, very low energy profile. And that's the power profile that goes with it. Again, you can see mostly off, with just peaks of energy coming in. Another problem that we've been dealing with is the measurement of the conditions of train pantographs. Pantograph is the part of a train that connects to the overhead electrical wire, running at typically 25 kilovolts and high current, 100 amps or something like that. So there's an enormous amount of power that comes through this into the train to drive the train. And one of the problems is the problem of maintaining the contact, and what happens when you have a difficulty with that. Now this is I've got a little video here, and I'm wondering if I can make it work. It might take me to just hit this here. Yeah. Good. Yeah. So this is a pantograph on a conventional track line here. Everything's working fine, and this is the way it should be. So we've put our optical fiber sensors onto this pantograph. This is where things start to go wrong. You can see that some of the difficulties that arise, that if you break up the pantograph, then you can have problems with the pantograph breaking, the connection failing, and it can sometimes take the line out. So what we're looking at is putting optical fiber sensors onto the pantograph. We're working with this group of companies here. These are the main manufacturers, and Network Rail are the people who use these. This is our test rig here. So this is what this pantograph looks like, and then we have our sensors mounted up here. We took this to an exhibition, a railway exhibition, just a couple of months ago, and there's our stand showing this actually in action. And we did some tests in December on this train here. It's a relatively slow speed train, and we were able to put the sensors on. So we've been using this in a closed loop system for improved performance monitoring, working with Bracknell Willis. And I think you could just see my colleague Professor Tom Sun here with Lee Brown, who's the representative of Bracknell Willis, just at that exhibition. And I think you can see this is the pantograph, and the sensors are up here, and then you can see this is just the optical fiber line running down at the moment. We'll be able to build that inside the pantograph itself. But it gives you an illustration of the problem and where the solution arises. So this is the pantograph on the articulated arm that you saw. And really what we've been doing is just experimenting with a number of different configurations of optical fiber Bragg grating sensors to measure the strain in this environment. And we have a test rig here in the laboratory For safety, it's a low voltage one. It's running at about 6 volts rather than 25 kV, but it's running at 100 amps. So we're getting the same heating, but at a much lower rate. And we're able to show some of the problems and some of the solutions. And you can see here just some of the sensors that we have built into the system. And then we're calibrating it in the laboratory with the use of different masses here, which provide the weight, and then we can look and see the way in which the force is applied across the pantograph itself. The force is typically about 19 newtons is the force, the ideal force. We want to measure that if it goes much higher, you've got a potential problem, and if it's much lower, you have a problem of it not making the connection. And we can measure that, and we can measure the position, and then feed that back to the train operator. Another area that we've been working on is fiber Bragg grating-based humidity sensors, and we make these sensors by taking an optical fiber with a Bragg grating in it, and we apply a polyamide coating to this, and that coating swells, and because the coating is in close contact with the fiber, then that swelling causes the fiber Bragg grating to expand, and we measure that expansion. So we have humidity giving a swelling of the polymer, which then provides a strain on the grating, which then gives us a shift in the resonance band of the grating. So we've been building some sensors in different configurations to do this. And so if you look at the reflectance as a function of the humidity, then you get a peak shift, and you can measure that and calibrate it. We produce these sensors ourselves, but we manufacture the gratings. We then coat these using this device, and the technique for doing it is as follows. You dip the fibers into the solution, you then swing it over and dip it into an oven and cure this at about 200 degrees, and you then repeat this, and indeed we're doing this for up to something like 40 to 50 coatings. So you gradually build up the coating, and you can change the sensitivity and the response time depending on the coating. So this is what it looks like. If you're close to the front, you can see this is an optical fiber, slightly yellowish due to the coating that's been applied. And then this is a stainless steel tube which holds the fiber itself. And this is just low humidity and high humidity. You can see the way the peak has shifted. So what have we been doing with these sensors? Well, we've configured them in different ways for different applications. What you need as well is a temperature sensor, because your humidity sensor will also measure temperature, and you want a separate temperature sensor so you can then unscramble the effect of temperature and humidity. And we have built some of the sensors like this. This is a stainless steel tube with just some grooves to allow the humidity in, and the optical fiber is inside this. So this is a euro 1 cent coin, so it's a small coin, and you can see something of the scale. We've looked at also with some colleagues in Germany some of the problems of measuring in sewers. I mentioned sewers were a problem because of the fact that you can get gas buildup, and we've got some sensors to measure the humidity in the sewers, and also to measure leakage, because the leakage of sewers is a problem. And we have configured a humidity sensor like this with our German colleagues. This is we use a fairly hard plastic called PEEK to configure the sensor with the outer coating here, and then underneath it we use a small Teflon membrane, and then underneath that is the optical fiber itself. So that's the package that we use, and we get a nice response between wavelength and humidity and good calibration. This is the one that the sensor that we use to measure leakage, and what it is, it's an optical fiber underneath here with a felt wick So that felt then absorbs the water and it stretches. And what we then have is a nylon thread wrapped tightly around that. And the thread then gradually bites into the fiber and causes a loss within the fiber. And so you see here for a couple of tests that with time, and it's quite slow acting, that gradually the loss changes as the sensor wets and then dries out again. And we can use that to measure the leakage. But perhaps the most interesting work is some work we've done over the summer last year on, and subsequently with a utility company in Australia, in Sydney, to measure humidity within a sewer. The problem that they have in this sewer is that you've got a large buildup of hydrogen sulfide. And hydrogen sulfide is a rather nasty gas, and it's there in conditions of high humidity. So what we were looking at was a comparison between the performance of a commercial humidity sensor, which is this device here, and this is a different configuration of our humidity sensor. This is one that we produced relatively quickly and cheaply using 3D printing techniques. So this is perhaps the more sophisticated version that I showed you a little bit earlier with the PEAK packaging and the Teflon, and then this is the quick and cheap version where the fiber is encapsulated and then 3D printed. And the results of this, I'll show you in a moment. This is this close-up of the end. You can see this brown staining on the fiber is the coating that we applied. So this is it in the sewer. We have two PEAK type sensors, two printed sensors, and in the middle we have, in this we have a conventional humidity sensor. And so we're able to compare the performance. And this is the setup. Here's our PC, our interrogation system, and lots of fiber to connect it to monitor. The results of some work we did over the summer here, over a period of about 10 days, you can see. So we have a very high humidity, about 95 to 100% humidity, in an environment where there's a very high level of hydrogen sulfide as well. So just to show we had the dynamic range that we expected, we dropped the humidity, and you can see we dropped it twice at the start, and then twice at the end, to prove that the sensor was still able to respond both at the start and at the end of the test. And if you look closely, you can see this, the result of the electrical sensor is the purple measurement here, and the optical sensor is the green. So you can see the optical sensor responds much more quickly than the electrical sensor to the change, both down and up, and in the end the two then eventually run into each other, so you get a comparison. This is after just a couple of weeks of test, and you can see this is the conventional sensor that it's been attacked by the acid environment and looks really pretty much in a bad way. And this is our sensor. You can see some of that on the surface, but underneath here is the actual working part of the sensor, the optical fiber, and it's working perfectly well. So the conventional sensor in fact failed within about 2 weeks, and our optical sensor was able to work. We left it, and we asked our colleagues in Sydney to inspect this after about 3 months, and you can see after 3 months you have even more problems with the conventional sensor here. These are the two PEAK type sensors and our two conventional printed sensors, our optical fiber printed sensors, and they're all looking okay. In fact, this is really the best design. I think you can see the effect of 3 months in a very unpleasant environment on this one is pretty limited, and it's looking good. So what we've been doing, we were in Australia fairly recently, and we brought the sensors back with us, and we've been doing a recalibration of these sensors And they've been in about 6 months now in this sewer, and we're recalibrating and testing them. They all work, which is good, and we're just checking that the calibration is what it should be. But I think the key messages really are that we have optical fiber sensors which have a faster response time and a better dynamic range than the electrical sensors, that the optical sensors are more durable than the conventional sensors, and that we have a level of sensitivity that's as good. So if you look at response time better, durability better, and sensitivity as good. So we have, I think, really a very satisfactory solution to what is a particular problem here in the tests that we carried out. And we'll be, we're just writing up some work on the evaluation of the sensors after 6 months. We've used these sensors to measure the problems of environmental degradation of limestone. The problem with limestone is that water gets into limestone. As it comes into the limestone, what it does is it carries with it chemicals. Those chemicals can then react with the limestone, which is just calcium carbonate. So if you remember your basic chemistry, a calcium carbonate plus acid just eats away and gives you carbon dioxide and other salts. And so we've been using optical fiber sensors to measure the humidity, and in that way to warn of the wetting of these limestone blocks. And working with colleagues at the University of Oxford, where they have limestone blocks which are 250 years old and even more than that, as part of some of the buildings at Oxford, then there is a significant problem. This is a new wall built with limestone blocks, and the one where we did our tests. And it's proved that the optical fiber humidity sensor works very well. And I won't dwell on some of those results. We've also used long period gratings rather than fiber Bragg gratings. And again, I'm running out of time, so I'll just quickly run through this. But these are similar types of gratings. They work in quite a similar way. What you get is a slightly different type of response from the way in which you get the mode coupling in the material. But basically, this is the spectrum. You get a broader spectrum, but one which shifts more significantly. I'll come to the particular result here that's important. We've looked at PVA versus polyamide as the material. And it's interesting, if you look at this scale, that in the high humidity region, around 80 to 100% humidity, then you get a very much greater response. This is the wavelength change with the PVA than with the polyamide. So that's good news. And secondly, if you compare the response, the wavelength change of the Bragg grating, which is this one here, with the wavelength change of the long-period grating, you can see that in the very high humidity gain, 80 to 100%, the long-period grating gives you a greater sensitivity. So again, there is more than one technique that you can use to try and solve a problem. And again, looking at our problems of landslides and erosion, again, just an illustration of the fact that you can use different techniques to monitor different problems. And it's just a matter of optimization, and this is a very good illustration of where this technique really optimizes. I think I've probably run out of time, but let me just go quickly through to this. This is a monitoring of a marine propeller. This is a full-scale marine propeller. It's about 2 meters in size across here. And what we've done is we've mounted on each blade 67 fiber Bragg gratings. So 67 times 5 means we have about 330 fiber Bragg grating sensors on this marine propeller. And the aim is to monitor the acoustic properties of the propeller, because it is something where the acoustic properties change very significantly as a result of very small changes in the design. again, Professor Sun here, and you can see the scale of this propeller. And the other nice thing about it is that you're able to make these measurements underwater. This is a tank that we have in the university, and here's the propeller sitting underwater. Now, if you compare with conventional sensors, first of all, trying to put 350 strain gauges onto this propeller is a very difficult task. Secondly, it will actually change the propeller so much because of the loading of the weight and the effect of these sensors. And thirdly, if you want to try and isolate them from the effect of the water, then you'll be spending an enormous amount of time trying to coat them in some sort of compound to do that. So conventional sensors really just don't work, whereas here we have a perfect illustration of where the optical fiber sensors are really beneficial for an issue like that. We've got some nice results, and I won't dwell on them, but I'll just come to the picture. And what we have for some of our gratings here is a comparison between a finite element model and the results of the optical fiber sensors. And really we're just using color code here and you can see from the similarity between the color coding with the finite element modeling and the color coding with the experimental work that you get a very good agreement. And we're currently looking at not just propellers but marine rudders again to understand their properties. So you can do this with the different types of really look at the different acoustic properties. We put optical fiber sensors into electric motors again to try and understand exactly their characteristics. And as I really have run out of time, I'll just flick through that. It's some very interesting work. It's ongoing, and it's particularly looking at the way in which we can monitor motors better. As electric motors are being used more extensively now in cars, then one of the questions is just what's their performance like? How can we make sure that their performance is as it should be? And the way to do that is to monitor inside the motors. Motors are electrically quite noisy and quite unpleasant, and optical fiber sensors work very well. So, conclusions. I would hope I can suggest that optical fiber sensors are practical devices for measurements in the laboratory and outside, and looking at erosion and landslip, then really you're measuring outside the laboratory. They can be fabricated fairly easily and used fairly easily. You can package them in different ways. You can design them in different ways. They've got good sensitivity, low mass, they dry out easily. They work well in different industrial environments. And I hope in the test that I've shown, you can see just some of the strength of what can be done. And obviously then extrapolating this into some of the work that we're looking at, and of course this means the new potential applications that there are. So acknowledging our funding agencies, and most particularly a group of students and postdocs who've done this work over a number of years and really contributed to this and what we've done, then I hope I can convince you that there is some real potential for the solution of the problems that we have with optical fiber sensors. We can take some of these techniques and extrapolate them. We can look at new techniques, but hopefully we can solve problems. And hopefully in a few decades, this building is still standing. The water hasn't come in, and we can say that optical fiber sensors have been the reason that we have been able to monitor and do things, and made sure that at least some of you might be able to come back here in 50 years' time and see that this building is still there. So thank you very much for your attention, and happy to answer any questions.
Thank you very much, Prof. Grattan, for the very interesting lecture on the optical fibers. So I know we already a bit exceed our time for tea, but because of the interesting presentation, I would like to open to the members of the floor if you have any questions. to Prof. Grattan. Any questions? Basically, I have. Actually, I have three, but I'll ask one. Or two. Alright, basically, I would like to know how does you determine the cost efficiency when you want to use the fiber sensor for any applications? Because as I can see, the applications that you are using is just for mega project.
Yeah.
Does it only for mega project?
I think not. I think you really need, I think, to look at two ways. One is, how does the optical fiber sensor compare with conventional sensors, assuming you could use them? And secondly, what is the cost of not measuring? So if you have a situation where you don't actually make that measurement and something fails, what's the cost of putting it right? And in many cases that can be very significant. It can be an issue of safety around people, so you could injure people, you could even kill people if you don't make the right measurements and protect the system. And secondly, something could be closed, and so a building like this may be unavailable for use, and that represents a cost to a company if the measurements aren't made. So I think it's for each case you do that analysis and work it out. But it is surprising what costs there can be when safety considerations aren't met, or where structures are not available for use. And so from that point of view, you can find optical fiber sensors can be quite cost efficient.
Thank you very much for that. Another one, do you see the optical fiber sensor to be in domestic application or appliances later?
I think it's possible. The domestic market, rather like the automotive market, is very, very competitive. I know in discussions with colleagues who work in the automotive sector that you might spend many tens of thousands of dollars on a car, and yet the companies are providing the sensors that have transformed the whole way in which cars work, are being challenged to produce the sensors for $1 or $2 each. So it seems a very big contrast. I think it's going to be much more difficult to see optical fiber sensors in a domestic environment when you can make measurements with conventional cheap sensors, and that's probably going to be the situation. Possibly in something like cars, you may well find that it could be economical to put a fiber loop in and put sensors in a fiber loop, possibly because of the weight saving, and I suspect that's going to be more important for cars which are high value, or even indeed looking at something like Ferraris, I think, or for racing cars, something like that. But the motor work that we're doing has an ultimate, is actually driven by a grant which is looking at the use of electric motors in aircraft. So, and that's really quite a way ahead. But in aircraft, weight is very, very important. So you can see that in an aircraft application, to contrast, say, with an automotive one, the weight factor from an optical fiber sensor can make all the difference in it being used. And so again, it's doing that detailed analysis that's important.
Thank you. I have another one. I open to the floor if anyone has questions first. Anyone? If not, I'll ask another question if you don't mind. May I know what is the current issues on optical fiber sensors? Maybe in terms of the materials or in terms of the,
Yeah, I think that there's a whole range of things really. The most challenging fiber sensors for us are chemical sensors, and I haven't talked about chemical sensors, where what we're doing is designing chemical coatings to go on optical fibers, and then you need to design coatings so that they bond to the silica of the fiber, and yet there is a chemical sensitivity and a good selectivity that comes from that. So what we're working with our particular chemist in our group who's designing those, and I think those are particularly challenging but they're particularly interesting, and I think there's lots of potential from that. So I would see that as one area, and I think Alberto will talk to you later on today about some of the interesting work in fibers of a different scale. And I think those present new challenges and also new opportunities. So I think when you get to the end of today, you'll see some of those contrasts and see some of the potential for how new materials, I think, can influence the way in which we can make new sensors.
Thank you, because we have with us some chemists.
Okay, good.
So that's why I think it's quite important for me to ask that question.
Good,
For
good.
our own, maybe we can contribute something to it. So thank you very much again, Prof. Grattan. A round of applause to our first speaker.
Thank you.
So ladies and gentlemen, based on the tentatives today, as you can see, basically we'll be having break after this. But before we go for a break, on behalf of the organizing committee, I would like to invite everyone for a photo session to commemorate this event. So we'll be having a photo shoots in front of the Roma University, and then we'll be having our tea break. And we'll be meeting here back at 11:30. Thank you.
That's it. Thank you. It says you can use that one or the yeah, that's sensible. Good idea. I find it in an airport somewhere.
Right, okay.
And actually, what it is, it was, I've had it for 7 years, and the previous computer it actually fitted into there was a slot on the computer that fitted into it. And that's why it's designed in this way. But actually, it's very, very handy that you can put it into this.
Is it credit card size?
It's credit card size, so you can put it in here and then it fits in all my accessories in this little pocket. So it's very, very handy.
And it has the laser pointer as well?
Yeah. So it's run from one of those flat cells or any type cells.
Because very often pointers they have that sort of size.
Yeah. But it's like everything else that you forget often to bring it with you.
That's your next job.
Oh, sign.
All of them.
All right. So you know what happens? You forget to bring something with you, and then you don't have words with that one because it fits in the pocket. It's always there.
And you have less troubles at customs. I had a colleague
yes.
who got his laser pointer removed in Canada.
Really?
Because they thought it was dangerous.
Oh yes.
Because of the powers involved.